Okay, so now we want to move into volume elements, and we're going to look at areas of known cross sections, or volumes using areas of known cross sections, I should say. All right, so this is in the XY plane. Okay, this is not a volume right yet, it's an area. Okay, but what I want to do is actually consider what would happen if I were to fill this region, fill region, with slices with square cross sections perpendicular to the x-axis. Now we're going to incorporate MATLAB to help us to see some of this, not in this video. I'm going to do my best to draw this in 3D. So if that were the x-axis and this were the y-axis, we're looking at a region. Actually, let me extend my x-axis further. We're looking at something that gets bigger and bigger in the y direction as we go further in the x direction. So the curve actually looks something like this in the x and y direction. Okay, and we would have slices of area that kind of go, these lines are parallel to the y-axis. So these would give me slices of area. But what this is saying is each one of these little slices of area has 3 dimensions to it. Okay, so let me take a slice right here. We actually have a square that is right here. Okay, and it has a little bit of thickness to it. It goes back there and back there. Let me put a back corner on this. I'll do it with dashed lines. It has a thickness to it that looks something like this. So it's a slab. Okay, and you can see this thing has 3 dimensions, and we're going to have more slabs as we move to the front. Further forward in the x direction, we'll get larger slabs. If we go further to the back, those slabs will get smaller. Okay, and we can put them all together and get an object. Now, right now, I'm showing a very large slab, right? If we make these slabs smaller, we'll get a very smooth, curvy object that is formed out of these slabs, right? The key is we want to focus on the volume element. Okay, so right now, this volume element is made of a square, which has a side of length s, right? So the volume of the slab could be the area of the face of it, the square, and a thickness. It's delta x thick, right? If we were going the other way, they might be delta y thick, right? So we want to be able to write what S is. Well, what is S? S is going from, it's a top to bottom. It might be helpful to look back at this picture here. Each one of those, that rectangle that I drew might be right here in the picture. And the height of this rectangle in the 2-dimensional base was the S value of the bottom. Okay, so that base is lying right in the XY plane. That would be the side length. So looking back at the 2D picture, that's the easiest way to see how big S should be. We simply have to take the top function minus 0, okay, in this case. So it would just be the square root of x is where the top is, minus 0, which is the bottom. So that's just square root of x. So that's what the volume element would be. And if I substitute back in, that gives me s squared is just x, delta x. And I could find the volume of this shape by integrating from 0 out to some value. Did we say where that was? We said 4. From 0 to 4, x dx. Right, and that's very easy. Take the antiderivative x squared over 2 and evaluate that on the interval from 0 to 4, and you get 16 over 2 minus 0. So we get 8 cubic units. We didn't say if the units were in centimeters, that would be 8 cubic centimeters, but we have 8 units of volume for that shape. Okay, so the key was being able to write what the volume element is. Okay, so it has a square face, so that has an area of s squared and a thickness of delta x. All right. So once again, the easiest way to know what S is to actually look at what's happening in the base of the object, because the 3D picture is unnecessarily complicated. The height of the square out of the page is the same as the height of the square in the y direction. Okay, so the height in the z direction matches the height in the y direction. So we can use this simple process to figure out the volume of the shape created by using square cross sections, right? Now in this section, we could have used other types of cross sections. So let me just show a few more, right? I have all kinds of choices. I could use rectangular cross sections, all right? But the one we're going to focus on is the equilateral triangle. Okay, so if we had used equilateral triangles, that would create a little ridge along the top, and a slab would look something like this. Okay, and let's see, I'm having a little trouble getting that far side. Let's see, so if it was slanted something like that, it would, then it would come down something like that for the far side, and this would connect over, all right? And assuming that we align them perpendicularly to the x-axis, this would be a delta x, all right? And we would have the side length, this was the base, okay? The base is still the same S that we had before. Okay. Now to find the area of a triangle, we all know that you take that delta A should equal 1/2 base times height. Oh, I'm sorry, this is now a delta V because it's a slab. So let me change that to a delta V because we're going to have 3 dimensions, a base times a height times a thickness. The thickness is delta X, right? So we can see B is the same as the side of the square. But what is the height? Well, pull out a little trig. Okay, this would be a 60-degree angle. Okay, so what is the height? It is going to be S times the cosine of 60 degrees, which anyone knows is √3/2. So we could say it's √3/2 times S. All right, so we could put all of that together and determine that the volume of a slab is 1/2 times √3/2, so that's √3/4 times s squared, base times height. You have an s squared there, and then you have a delta x. And so if you want a volume integral, you would just integrate. If we're using the same function, if we are just filling with triangular slabs, we would integrate from 0 to 4. We might want to put the constant out front. You can leave it in the integrand, but it's more elegant to bring it out front. Oh, and what was s? In s was the, so it'd be s squared times dx, and in this case, s was the square root of x, so the volume would be √3/4 times the integral from 0 to 4 of x dx, right? A very common other shape would be using semicircles. So if I took a semicircle, it's going to go back a little bit, okay, and you're going to have this semicircle in the back. I probably will butcher the way this looks. Okay, this will have a top kind of extending back, something like this. So it probably, you're going to kind of see a little bit of a 3D shape here. I'm just going to kind of shade this in. That's about as well as I can do. So there we go. On the inside, it would look something like that. But here would be the base again. The base is the same base as we had before. What's important to note is, as a semicircle, there would be a radius that way and a radius this way. And you can see the radius is half of the base. If you wanted to find the area of this element, the volume of this element, there are 3 dimensions. You have a circular front, but it's half of a circle, so it's half pi r squared would be the area of the front times the thickness, which would be delta x. And so r is equal to s over 2. So delta v is equal to 1/2. Actually, it'll end up being 1/8 pi s squared. When you square s over 2, you get s squared over 4. So we end up with 1/8 pi s squared delta x. If s is the square root of x, s squared will be x. So delta v is 1/8 pi x delta x. You can turn that into a volume integral, the integral from 0 to 4, we'll assume again. And what can you do? You can put the pi over 8 in the front as a constant, pi. Oh, let me clean that up a little bit. So that's an 8 in the denominator. You have 1/8 pi, which mathematicians most commonly write as pi over 8. I'll write x dx. So the only difference between this and the integral that we already did was the factor of pi over 8 out front. Okay, so it'll be the same answer multiplied by pi over 8.